And now we're going to make inferences from two samples. And the first thing we want to do is we want to test inferences about two proportions. The objective is to test claims about two population proportions or construct confidence intervals to estimate the difference between two population proportions. So those are the two things we're going to do. We're going to run hypothesis tests, and we're also going to create confidence intervals. So here's some of the notation that we're going to be using. Um, we have P1, because we have two populations now, we're going to use a subscript of 1 to denote the proportion from the first population. And N1 would be the size of the first sample, and X1 would be the number of successes in the first sample. So when the subscript is 1, we're talking about the first sample um, from the first population. And the corresponding notation for that is P2, the proportion from the second population, N2, the sample size of the second sample, X2, which is the number of successes in the second sample, and let's see, we have P hat 1, which is the sample proportion of the first sample, which corresponds to P hat 2, the sample proportion of the second sample. We have Q hat 1, which is 1 minus P hat 1, and Q hat 2 is 1 minus P hat 2. These are the complements. So these are the notations for population 1 that are listed, and the corresponding notations for population 2 are over here. Now, notice these are identified by which population they come from, but there's also the pooled sample proportion. The pooled sample proportion, denoted P bar, is basically the proportion that you get when you mix the samples. So if you take the two samples, add up the number of successes, add up the sample size of both, and then make the ratio of those, that proportion is going to be P bar. So it's basically the grand proportion for the entire sample. All right, so we have that pooled sample proportion, the pooled sample proportion, and we have each individual sample proportion. So we have three sample proportions that we are looking at here. Now here are the requirements. The first requirement is the sample proportions are from two simple random samples. That's simple random samples that are independent. Okay? And the second requirement, for each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. If you remember, those were the requirements for using the normal distribution as an approximation for the binomial distribution. And that makes sense because what we're talking about here is a number of successes and failures, which would make this a binomial trial. But we're actually using a z-test statistic, so we are actually going to have to use the normal distribution as an approximation for the binomial. All right, notice this is the test statistic actually. And this test statistic is a little bit more complicated than the ones we've been dealing with so far. It's the difference of the sample means minus the difference hypothesized in the population, or sorry, the difference of the sample proportions. We're not dealing with means. Is the difference of the sample proportions minus the hypothesized difference between the population proportions. But remember, we're testing the claim that P1 is equal to P2. So if P1 is equal to P2, then their difference is 0. P1 minus P2, you subtract P2 from both sides of that equation, you get this equation. P1 minus 2 P2 would be 0. So this term, or these two terms, that subtraction goes to 0. So really, what we're doing is calculating this for this particular null hypothesis. The numerator is then just P hat 1 minus P hat 2. And the denominator would remain the same, but the reasoning is because we don't have to necessarily be testing the null hypothesis that they're equal to each other. We could be testing an alternative hypothesis, for instance, that one proportion is greater than the other, or that one is less than the other. And in those cases, we wouldn't actually be looking at this particular null hypothesis of P1 equaling P2, but the book is simplifying it for us, so we're actually going to be able to use this as our test statistic, because that second pair of that second difference actually is 0. Of course, we have the pooled sample proportion, and because this is a z-score, we can get a p-value from table A2, or we can use TI-83 or 84 calculator. And the critical values are the same because this is a z-score. So let's see. This is how we're going to construct a confidence interval. Now remember, we're constructing a confidence interval for the difference between the two population proportions. So the parameter that we're trying to estimate here is not P1 or P2, it's actually the difference of P1 and P2. So this is the parameter that I'm trying to estimate. And in order to do that, we're going to find a point estimate. Well, the best point estimate for P1 minus P2 is P hat 1, the sample proportion from sample 1, minus P hat 2. So this is the best point estimator for the parameter P1 minus P2. All right, and what we're going to do is we're going to find that point estimate, and we're going to add and subtract a margin of error. And the margin of error is going to be found this way. Here's the uh, formula for our margin of error, E. This can actually also be done on the calculator. We can use that formula, or we can just plug it into the TI 83 or 84. So let's go ahead and look at some examples. Now remember, the hypothesis test, for a test of hypothesis made about two population proportions, in our book, in our class, we're only going to consider the ones that have the null hypothesis that uh, P1 is equal to P2. All right? Those are the only ones that we're going to actually consider. Okay, so let's go ahead and look at this example 8. It says, in exercise 7 and 8, assume that you plan to use a significance level of 0.05, alpha is equal to 0.05 here, to test the claim that P1 is equal to P2. Use the given sample size and number of successes to find A, the pooled estimate, B, the z-test statistic, C, the critical values, and D, the p-value. All right, we're going to go through, we're going to find all of those things. All right, so the first thing they want me to find for part A, they want me to do the pooled estimate, P bar. And if you remember from above, P bar was equal to x1 plus x2 over n1 plus n2. So what we need to do is we need to identify the x's and the n's. We need to identify the number of successes and the number of trials for each sample. So let's move this guy down a little bit here. All right, so let's see. It says Chantix is a drug used as an aid to stop smoking. The number of subjects experiencing insomnia for each of two treatment groups in a clinical trial of the drug Chantix are given below. So we have the number in the group in the top row and the number experiencing insomnia in the bottom row. So basically, out of this many people in the group, 19 of them experience insomnia. So we'll call this sample 1. Sample 1. Sample 1 is the Chantix group. All right, and we'll call this one sample 2, the placebo group. Sample 2. All right, so the subscripts of this group over here that's under sample 1, the subscripts are going to be 1, and the subscripts of the group under sample 2 are going to be 2. And the number of successes, or the number of people that had insomnia, x1 is 19, and n1 is equal to 129. So we have x1 and n1 given here in the problem. And we have x2 here, x2 is equal to 13, and n2 is equal to 805. So the pooled estimate then is going to be x1 plus x2, 19 plus 13. That's actually the total number of people that experience insomnia. And then n1, which is 129, plus n2, which is 805. And that's actually the total number of people that was in one of the two trials, in either trial, the total sample size. So we get a value of 0.034. 0.034. And we've answered the first question. The first part was to find the pooled estimate p-bar. Now, part B is to find the z-test statistic. Find the z-test statistic. Well, you look up here, the z-test statistic is given by p hat 1 minus p hat 2 over the square root of the product of uh, the pooled p over the pooled q over n1, or times the pool q over n1 plus the pool sample proportion times the complement of the pool sample proportion over n2. So we're going to use this formula to calculate our uh, z-test statistic. All right, so let's see. Our z-test statistic, it says, is equal to p hat 1 minus p hat 2 divided by the square root of p bar q bar over n1 plus p bar q bar over n2. So let's see if we can't find these numbers. Well, let's see. Um, the things that we haven't found yet, we haven't found p hat 1 or p hat 2 yet. We need those in order to calculate the formula. We have p bar and we would also need q bar, but that's not going to be bad because that's just 1 minus p bar. So those are going to yield for us p1 of 0.147, 0.147, which is 19 over 129, P2 of 0.016, which is 13 over 805, and Q bar of 0.966, which is actually 1 minus 0.034. All right, so doing these calculations, let's see. We have P1, which is 0.147, minus P2, which is 0.016, divided by the square root of, and then we'll have P bar times Q bar, which is 0.034 times 0.996, 0.996, oops, 0.966, not 0.996, so let's see, 0.966, and then we're gonna have divided by n1, and n1 is 129, and then we're gonna add that same product, 0.034 times 0.966 over n2, which is 805. And all right, let's see what we get for this calculations here, for these calculations, which is approximately 7.62. 7.62. All right, so let's see. Now we have our pooled estimate. We have our z-test statistic, critical values, and p-value. All right, to find the critical and p-values, we can actually use the TI A3 and or 84 calculator. So let's bring over the TI over here. All right, now the p-value, or sorry, yeah, the p-value and the critical value, or the critical value is actually a z-score that separates the rejection region from the area where we would fail to reject. So let's find the critical value first. The critical value. So let's see. We're gonna need to use the inverse normal function on the calculator. So we're gonna go to, well, let's turn it on first and let's clear it. We're going to go to second, distributions. We need the inverse norm because we're looking for a z-score. Inverse norm. And the critical value is actually going to be 1 minus alpha. There's the inverse norm of 1 minus alpha over 2, since we're doing here a two-tailed test, because the null hypothesis is that P1 is equal to P2. So the alternative is that P1 does not equal P2. And we have our significance level of 0.05. So we're going to go ahead and we're going to find the z-score for 1 minus, oops, not negative. We're going to find the z-score for 1 minus, and then we're going to do the alpha, which is 0.05 over 2. So this is how we're going to find the critical value. We're doing it all at once instead of doing it step by step. But we've done this quite a few times before. It's the inverse norm of 1 minus alpha over 2, or the area to the left. And we get 1.96. So the critical values, since it's a two-tailed test, are 1.96 and negative 1.96. So for part C, for critical values, critical z values, we have negative 1.96 and 1.96. We would utilize those numbers if we were trying to do the traditional method, and based on that, we already see, because of the test statistic and the critical values, we would reject the null hypothesis, because basically we have that the critical values separate the rejection regions from the region where we would fail to reject. 1.96 and negative 1.96. And the rejection regions are over here on the tails. And our value of 7.62 falls well into the rejection region, way out here at 7.62. So it's extremely large for a value if the null hypothesis is true. So based on the traditional method, we would reject our null hypothesis. Now, the p-value method is going to give us the same conclusion. So let's look at D. But remember, they're asking us to calculate all these things, but they're actually two different methods. If you're finding critical values, you're not necessarily going to find a p-value. And if you're finding p-values, you're not going to find a critical value, because the critical values are from the traditional method and the p-value is from the p-value method. So let's go ahead and find the p-value here. All right. So the p-value, we take out our ti. All right. And what we're going to do now is on the, oops, ti disappeared. Let's get the ti back. What we're going to do now is we're going to, instead of the inverse norm, now we want a normal CDF, because now we have a z-score and we want to find an area. So let's see. We're going to go to distributions and we're going to go to normal CDF. Now what the p-value is going to be twice the area to the right of our test statistic. So we need to find the area to the right of our test statistic. So the left z is actually our test statistic, 7.62. Oops. Is 7.62. 7.62. And the right z is infinity. So I go second, E99 for infinity, and I press enter, and it gives me this z-score, which is 13 zeros and then a 1. That's a very small number, and we multiply that by 2, or not that z-score, they give me that area, or that probability. We multiply that by 2 and we get 13 zeros with ending with a 3. So that's a decimal point, 13 zeros, and then a 3. I'm going to write that in scientific notation as 2.6 times 10 to the negative 14th. So that's going to be our p-value. P-value, p-value is equal to 2.6 times 10 to the negative 14th power. Now that's a very small number. That is going to be less than alpha, which was 0.05. So once again, in this case, we would also reject the null hypothesis. So the traditional method and the p-value method are aligned with each other. All right, now let's take a look at this last example here. And for this example, we're going to use the TI to do the whole thing. So let's take a look at it. There are two examples here, actually. It says morality and marriage. A Pew Research Center poll asked randomly selected subjects if they agreed with the statement that it is morally wrong for married people to have an affair. Among the 386 women surveyed, 347 agreed with the statement. Amongst the 359 men surveyed, 305 agreed with the statement. Use a 0.05 significance level to test the claim that the percentage of women who agree is different from the percentage of men who agree. Does there appear to be a difference in the way women and men feel about this issue? Okay, so we're going to do a hypothesis test here, and we're testing a hypothesis about the proportion of men versus the proportion of women who believe that it's morally wrong for married people to have an affair. All right, so what we're going to do is we're going to collect all our information, and then we're going to put it into our TI. So we'll have the women and the men as our two samples. X1 and N1 will be for the women. X2 and N2 will be for the men. So the number of successes, or the number of women who agreed with that statement, was 347. The total number of women, 386. The number of men, the number of men who agreed with that statement is 305. And the total number of men, 359. All right, now let's see, is there any other information I can gather here? We have a significance level of 0.05, so alpha is 0.05. And we're testing the claim that the percentage of women is different than the percentage of men who agree with this. So we're testing the claim that P1 is equal to P2. This is our null hypothesis. Actually, the claim is actually that the percentage of women who agree is different. So this isn't the claim. This is the null hypothesis. Is that that there's no difference. That the percentage of men who agree is equal to the percentage of women who agree in the population. The claim is actually the alternative hypothesis, which is that somehow the proportion of men who agree with the statement and the proportion of women who agree with the statement is different. So the alternative is that P1 is different or not equal to P2. So there we have our null and alternative. This one is actually our claim. And what we're going to do first is we're going to do a hypothesis test. All right, so let's go ahead and bring out the TI. And here are the directions for our hypothesis test. Uh, we're going to, um, well, let's bring it down here. Extend the page and bring it down here. All right, so we're going to get out our TI, the TI-83, and we're going to we're going to follow these directions to do the hypothesis test for the proportions. So it says we can go to stats, press stats, and tests. So we're going to go over the tests. And we're either going to do 2 prop z test or 2 prop z int. If we want an interval, we do the z int. If we want a test, we do the test. So we're looking for 2 prop, which is 2 proportion z test. So here it is, number 6. Number 6 is 2 prop z test or 2 proportion z test. And I press enter, and it's asking me for all the things I have here. X1 is 347. 347. N1 is 386. 386. X2 is 305. 305. And N2 is 359. 359. And then it's asking me for my alternative hypothesis. The alternative hypothesis is that the proportions are not equal. And then all I have to do is calculate. And it gives me all this information. It's giving me my z test statistic. This would be the test statistic. So this is slightly more than 2 standard deviations. So it's on the borderline kind of an extreme value. Not extremely extreme. Well, not very extreme, but extreme nonetheless. Unusual nonetheless. The p-value. The p-value. Now, this might get a little confusing because there's 3 p's here. P hat 1 is the first sample proportion. So this is the proportion of women who think that it's morally wrong to have an affair. This is the percentage of men from the sample who think it's morally wrong to have an affair. And this is the pooled. This is x1 plus x2 over n1 plus n2. So even though there are 4 p's, the very top one is the p-value, the one under the test statistic, and that's the generality. The p that comes right under the test statistic is going to be the p-value for that test statistic. All right, so we have our test statistic, our p-value, we have p hat 1, p hat 2, and we also have the pooled proportion. All right, so let's record those and make our conclusion. Let's see. We have that the test statistic, test stat, the test statistic is z equals 2.03, 2.03. The p-value for that test statistic, the area, twice the area to the right of that test statistic would be 0.04. 0.042 actually. That's a p-value. And based on this p-value being less than alpha, which is 0.05, we are going to reject the null hypothesis. Reject the null hypothesis. What that means is that we're rejecting the hypothesis that the proportion of men and the proportion of women, or the proportion of men and the proportion of women who believe that it's morally wrong to have an affair is equal. So somehow there's a difference between the proportion of men who believe it's morally wrong and the proportion of women who believe it's morally wrong. I wonder in which direction. Anyway, the next thing we want to do is we actually want to construct a confidence interval for this exact same data, but we rejected the hypothesis, which means that we actually have enough information to support the claim that is the proportion of men to women who believe it's morally wrong to have an affair is equal. So basically, we are actually saying that it's probably not equal, the proportion of men and women who believe it's morally wrong to have an affair. Now, let's do the confidence interval. To do the confidence interval, let's bring back out let's do the confidence interval. Let's bring back out the TI 83. We're going to do our confidence interval now. All right, so here's our TI. Turn her back on. Let's clear all that data out. Now, the thing is, this calculator is pretty smart. It's going to save all the numbers we had in. So we hit stats, we go over to tests, And in this case, we're going to do a 2 prop z int. So here we have a number, letter B. Letter B is 2 prop z int. So I'm going to press enter. And it's going to have all the numbers I just put in because I just did a hypothesis test for the exact same thing. And we go down, and it's actually a 95% confidence level because alpha is 0.05. Remember, the confidence level is 1 minus alpha. And then we just hit calculate, and it gives us our confidence interval. So 0.0017 to 0.097. All right, so our confidence interval is 0.002, let's call it, to 0.097. Now notice this confidence interval does not contain 0, meaning that since 0 is outside of the interval and we have a 95%, um, we're 95% certain that the true proportion is actually, or the true difference in proportion is actually captured on this interval, that means that 0 is unlikely as the actual difference. So we can actually look at the confidence interval and see how likely or unlikely it is that 0 would be the actual difference between the proportions, and we can get an intuitive feel of what's going to happen when we run the hypothesis test itself.